Okay, so y'all have any questions first, or that's good because I probably don't have any answers. Yeah, and I think I got the. I was going to send an email and I forgot. Um, but let me go out there. I think it's there. Have you looked? Is it there? This for Sunday. Okay. Man, it is really, really awfully slow. Okay, okay, okay. Right, we got that far. Okay, so I guess I can look at the calendar. If I look at the calendar, oh wait, I've never tried to launch it from the calendar. Okay, now the problem is I don't know which one's which. That's not that one. It's not that one. It's that one now. I don't know how to access it from there for me. You probably can be able to, you probably can just touch it and it goes from there. Gosh, I've been out of it so much. I need to see what I did assign. Okay. I hope I was planning just to do one. Let's see what oh, bad gateway. Uh, what is that all about? If I could just edit this. Okay. I'm not going to add anything, but it should tell me what the thing was. Come on. What is wrong with you? Where is it? Okay. Tell me bad gateway again. Yeah. I just did one because I've been sort of out of it and I didn't want to, you know, I figured I missed, I don't know what I missed. I missed a lecture somewhere in there. And I thought, well, I'll just do one as a follow up and then we'll move on into the next chapter after this. So this one, I guess, is just wanting to know all the velocities and everything. Pretty simple. Here, I'll just spend just a minute setting up an approach with it. Uh, uh, man, everything is slow for some reason. So on this one, if you just got, maybe it's the computer, but it's maybe a combination of the two. So if you got a velocity that's heading this way, yeah, and then this thing coming out and heading that way. And if you come out and grab perpendiculars to either one, that's not a, it is not a, that's supposed to be a straight line. Yeah, this is the party. This is the dynamics party. You go upstairs and get some money from the business and get some trinkets, food. So there's your perpendicular line. I tell you what, let's do this. Since I'm spending the time to draw lines, let's let's see if we can do it like that. There's one line perpendicular to the velocity on this link. And then there's the other line that's perpendicular. So your instant center sits right there. And then that's all you're doing is working off that. You could either do one of two things. I mean, if I were faced with this and given a problem, I'd use that, what was it called, GeoGebra or whatever? Put in the coordinates, double check myself, and then all you've got to do is find your distance. There's your omega. There's your distance from the instant center to B. And there's your distance from the instant center to C. And then velocity of B is just equal to omega BC times the distance from the instant center to B. And then velocity C is equal to omega BC times the distance from the instant center to C. Since you know that, you can find this after, of course, you found this from your geometry and that from your geometry. So since you were given that, that's what you would find first. That's supposed to be the number one. Well, okay, so here's what, let me see if I can get some of the excess information off there. What I would do, let me see if I can, I'll use a green and then get rid of that. Okay, hang on. Yeah, that's good. So all you're doing, gosh, this is an awful looking triangle. But if I select it and look at it, what do I got? I've got one thing, which I know this distance is 0.45 because of that. And then the other thing is, I think if you stare at it real close, you'll see that that's 45. So I know my drawing is awful, but this is going to be 45. Okay, okay, this is an awful drawing, but that being straight horizontal, if that's a good way to say it, that means that's 45. So really all I need to know is one other angle. Because if I know my distance, okay, so law of sines would be 0.45 over a sine of 45 equals to, this would be distance CB. This would be distance ICC. Now, the other thing is if you look at it, okay, let's think about this. What else can I do here? There is the fact that I've got this triangle as well. And if I pull that triangle off, you know, it will fit right there. So what can I figure out about it? First of all, I can figure that, oops, I can figure that. Well, right now we're trying to solve what he was asking, which was how do I find this and how do I find that? But in this problem that's on the thing, it says, I think it wants to know every single, okay, where did it go? It wants to know, okay, hang on. And now, oh, here. It wants to know first the omega of W. It's got to be the wheel. Oh, there's no other. I thought there was another question. Oh, okay. Okay. So to find the angular velocity of the wheel, all you got to do is find this velocity right there, and then the velocity of v is equal to omega of the wheel times that, which is 0.15. So your biggest deal, your biggest thing in the way is, like he said, is this, finding that and finding that from this geometry. So let me think about this. So what do I know? Can I do this? Okay. I'm finding all the different triangles that I can work with. Got that one. And then I've got this one. So of all those triangles, now me, I hate to kind of bring this up, but I would turn and use the S's and find out the values there. But I don't, I'm kind of hesitant to do that. So how would you, what else do you know here? There's got to be something else you know. You've either got to find this angle or this angle. So any ideas how you'd find that outside of measuring it or putting it in GeoGebra or whatever?
If you have the radius of the wheel, couldn't you attach two triangles like you mentioned earlier, and then use if you know the distance that one side of the triangle to make that into a right triangle?
Yeah, I think so. That and that. So I don't know which one would be most beneficial, but
I think that would be
this one.
Yeah, if you can attach that to the other one, and you have a distance, you can determine that angle right at the top is also 45.
Yeah.
And then work from that to figure out the rest of the length. Because then you have two angles and a side of that triangle.
Okay, so which is the other side? The point, what is it, 1.5?
Yep.
Okay. Hey, hang on. I tell you what, let me just do it that way. 0.15. So what's the angle you think?
The angle on the inside of that is also 45.
This right here?
Yep.
Okay.
If you were to attach that piece to the other one, you create a 45-45 90 triangle.
Yeah. Yeah, and that was kind of the one I sort of grabbed, but I don't know what I did with it. Oh, this one. So that one.
Well, I meant if you were to just attach that one that you have on the right to the original triangle, the green one.
Oh, okay. You're talking about like that.
Then you
Yeah.
create that 45, 45, 90 with the lower right hand corner and the upper corner.
Yeah. Yeah, you're right. So if you did that, okay. So what happened to my? Okay. So if you did that, ooh, okay, that was unexpected. Okay. So if you did that, okay, so if you had that, you would have this one and 45. This one, you could find that. Your first thing with law of sines. So if you did law of sines, the first thing you'd find is that one. Then what you could do is roll around. You know, everything's got to be 180. That plus the angle you found plus this got to be 180. So
you could also just, if you solve for the unknown side length of that red triangle, then you can immediately solve for the SPP.
yeah. Okay, hang on. I think he asked the question, what was the law? So the law of sines is the sine of that angle over its opposite is equal to the sine of another angle in the opposite. Although, come to think of it, you got this one, that's the length, and the opposite is that one. So it would be sine, how about I call them just theta 1 over 0.15. So that's kind of the law of sine. Law of cosines, you have two lengths and an angle between them, and that'll get you the rest. So, so you can work your way through and find that. And then if you wanted to check it, you could do the GeoGebra or whatever. And then if you wanted to do something bizarre, like I was saying the other day, I'm almost hesitant to do this, but what the heck, you know, you can start a vector. This is going to sound weird. So let me redraw the triangle. I know I have it in green right here, but I'm going to spend a minute and try to draw it. Well, now, because if I complete it, I'm going to do the best I can with my free hand. Okay, now what I'm going to do is kind of weird. And I know it's weird. Okay, am I copying? Yeah, I'm just copying the triangle itself. And I know this is weird, but if you, oh, wait a minute, escape. If you take a vector, I meant that to be a different color. If you take a vector that starts here and is a unit vector, and then you take a vector that starts here and then is a unit vector, say unit vector 1 and unit vector 2, and then you set up a coordinate system. This is going to sound really weird. Set up a coordinate system. And I'm not suggesting you think like this, but a mathematician might do that. So if you're going to draw a vector on this line anywhere, say this point right here, R on point 2, let's say R to point 2 is going to be this vector, which this vector, do we know that? We know it's that length, but we don't know exactly where it goes to unless we can find that physical point can we find that physical point? And actually, like what you were saying, you actually can. You can draw a vector here up to this, and draw a vector down. So you draw a vector to here, and you draw a vector back down 45 degrees. You can get to that point. So you can do R2 is equal to this vector, R to point B, plus some distance times U2. And it turns out you can do this for the second. If you're drawing a point along here, that R to location 1 will be just some other distance. We'll call that distance 1. This is distance 2, U2. You set them equal. In other words, as I slide this point out there, here, eventually there's one location that they'll equal, and that'll be the instant center. And it turns out if you just solve them, RB plus distance 1 times U2 is equal to distance 2 times, that was supposed to be U1. Then what you find out is that ends up being the distance from the instant center to C, and this one becomes the distance from the instant center to B. And you solve them directly. That's a really weird way to do it, and I should make an entire video on how you do that, but I'm not sure that's any easier than the other way. It's certainly not easier than drawing it on the what's it called, GeoGebra. But then once you got that, you're done. Because you've got these two distances. With this distance, you got that distance. You're working your way through it, and then you're taking this velocity B, put it back there, and you're done. So I should have given more than one problem, but since I've been out, I've lost a lecture along the way, and I thought, well, we'll just do a light week because next week we'll start back in on the next chapter, which I could just give you an overview of what's left. Maybe I'll do that, and then we'll, before I do that, is any other questions? Or this, like I said before, for me, I mean, the way I view this is these problems are the problems that are more likely to be done by an engineer. So that's the reason I spend more time on 16. Then essentially we've got 13, 14, and 15. And I can tell you what those are in about 5 minutes. And I'll just go ahead and do that if you don't, if you're okay with that. Or if you want to go, I mean, but 13 is, hang on. Chapter 13 deals with, okay, so 12 dealt with finding acceleration, velocity, and position. You had regular coordinates, you had X and Y, and then you had an R and a theta, a polar coordinate. And so we dealt with that. We dealt with polar coordinates. We dealt with B squared over R, or in his book, I think he called it rho. We dealt with all that. The key was we were essentially targeting or going to use this in 13. And all we're doing there is sum of the forces equal mass times acceleration. Now the key is you turn around and which coordinate you're using. So if you're using polar here, you got to use polar here. If you're using regular Cartesian X and Y, and I'll say Z2, then you got to use X and Y and Z here. And it's that simple. The problem comes in something like this, like, okay, so in a polar coordinate, let's do something. I'll show you an example of something that can cause a little bit of distress, but not that bad. Let's say you had a marble that was set to roll up this weird surface. So I'm making it kind of weird, and it would be such that R would be a certain value and theta might be a certain value, but R would be a weird function of theta. So this might do something bizarre. It might, I'm just making stuff up. So it does something weird like that. And then what you did is somebody welded a rod right here. And this rod went out. I'm just trying to avoid that. So here's a rod, goes out here and does like this. I just made it so it avoided that that little thing. It was pinned right here, and it was spun up at a certain, well, he actually may say theta as a function of time, and out of that you would get omega, or out of that you would get theta dot, which is the same thing as omega, and out of that you would get theta double dot, which is the same thing as alpha. And then he may say, okay, what's the force that this funny rod here has on this ball? And at first glance, you might think, oh, geez, now before, all you did was find the acceleration. Now, you got to do something really strange. And through the magic of these, being able to use this, you would have a force that would be perpendicular here, and I'll pull all these off. And you're going to have a force that is perpendicular to the tangent of the path. And then you're going to have a weight like so. So you're doing a free body diagram, and if you want to, oh shoot, that was the wrong thing to hit. Okay, if you want to, here's what you could do. I'll go ahead and include that. Include that. Okay, so if I do a copy, move to the side, and do a paste, see a free body diagram. And there's your free body diagram. The deal, this part on the free body diagram isn't part of the thing, but it gives you a direction where this should be. In other words, that has to be that. And then you've got, without too much, okay, so here I go. I'm drawing this to the center here. And then I'm going to select it and get it out of there. And now, unfortunately, I got to do this. I got to move this over because it's kind of gotten tight in there. And suddenly, you have your coordinate. Oh, wrong button, wrong thing. Okay, so suddenly you have your theta, and you go out here, and you have your base vector in the r direction, and perpendicular to that, you've got your base direction in your theta. When you solve your acceleration, you're going to end up with an acceleration in the r, an acceleration in the theta. So what do you have to do? You got to do something interesting. You got to do this. First of all, you got to get rid of that thing right there. You multiply times the mass of the ball, and equals to the force, sum of the forces in the theta direction, sum of the forces in the r direction. So what you have to do, here's your r direction. You've got to break these forces into their components. Along the r, along the theta, you got to do that with this too. Along here, along here, and you got to do that with this thing too. You got to break part this way and part that way. I didn't do that quite right. They're watching movies next door. And so what you do is you take, I should have done those in different. So for your R, for your R, you're going to have this one, actually, here, let's do it this way. Shrink this thing way down. So you're going to have this one right here, this one right here, and this one right here, all participating in the R. And then what you're going to have in the theta is you're going to have this one right here, this one right here, and this component right here participating in the theta. And so what you're going to do is the geometry is going to be a difficult thing. But I'll give you one of those, and I'll maybe two of them, and what I'll do is I'll show you in class how to break that down, and then when you start doing it, it makes a little better sense. The other thing that's a key here, and he does something weird in the book that essentially is very difficult conceptually, but let me ask you this question. And this question is key towards understanding this. Can you tell me, okay, so you know this is the path, right, that this ball is, and somebody would give you that equation. It would look funny like this. R is a function of theta. It'd be some equation in which if you plotted it, it would be this path. But you know this ball is touching on that path. So you know this is 90 degrees to that. Can you tell me how you would find that path? So if you had a particle, and generically, if you had a particle that went down that path, what do you know about, if you could find, and in this case you can, what would be tangent to that path? Wouldn't the velocity be tangent to the path? So at all times, velocity is tangent to a path. There's something really strange about this, because no matter what you've got, let's say you come up with here. Let's say you had a velocity. I'm just going to make something up, okay? 3i plus 4j. If you draw that on an ij, it doesn't matter whether it's 3ur plus 4u. It really doesn't matter what it is, which base system it is, it doesn't matter. So let's just use the x and the y. Okay, I'll draw 3 out here and a little higher up here. So there is that vector, just a standard vector. If you want to know something that is perpendicular to that, how do you find that? Believe it or not, it's something really incredibly simple. Whatever this, I'll call it P perpendicular vector to V is, all you do is you swap the coordinates. So where I see a 4, I move it to there. And then what I do is I'll make one of them negative. That's all you have to do. Now the key is how do you know that's perpendicular? And the way you do is use perpendicular to V dotted with V would be 4 times a 3. And this is what makes it so incredibly simple. 3 times a 4, but one of them became a minus. So automatically it becomes 0. So to find the perpendicular to this, all you have to do is find the velocity, whether it's in this coordinate, doesn't matter what coordinate system it is, it doesn't matter. All you do is the perpendicular here to this V, this one, is nothing more than 4UR minus 3U theta. Or it can be minus 4UR plus 3U theta. Doesn't matter. So he has a really bizarre way in the book of finding this tangent, of finding that vector. And it, to me, I look at it and I'm thinking, why are you spending that extra time? Because the velocity is always tangent. And if you want to find the direction of the other one, you just flip the two things and make one of them minus, and you've got the direction of this vector just like that. And so along the way somewhere you're going to have to unitize this. So you're going to have to turn this into a unit vector, but you already know how to do that. So that's what happens that's the hardest problem in 13. The rest of them are really simple. I mean, okay, so let's say you got a box. You push on the box with a certain force. It has an acceleration. Say the acceleration, you got a number. Okay, the acceleration was 2.5. The box was 10 kilograms. What's the force? It's just 25. It's such a simple, the rest of them are so simple. This is the tough one. These are the tough ones. The rest of them are so simple. Cannonball parabolic motion doesn't appear in 13. So really all you've got is finding the acceleration, multiplying times the mass, and the difficulty comes in these type of polar coordinates like that. And I'll work one of those. That's it. And then what happens in 14 is incredibly simpler. It's so simple, it's almost scary. But he breaks it into two parts. One is, it's basically energy. And he breaks it into two parts, conservative and non-conservative. And all it is you'll see this, 1/2 mv squared a lot. You'll see mgh a lot. 1/2 k delta squared a lot. And then you'll see this term F dot D. And this is kind of critical towards understanding whether you're putting energy in or taking energy out. Actually, you can use this to derive this one, and you can use it to derive that one. And he does that, and I'll kind of mention that. But this is just the kinetic energy. And these are, if you think about it, the weight of an object, weight is just mg. And if you're moving a distance h, then F, which would be mg, times the distance you moved it would be h, is actually that term. And then in the spring, the problem is, as you go, here's your spring stiffness K, it's not linear. So in other words, if you take a weight and you move it up a foot, at the top of the foot, the weight remained the same as it was at the bottom of the foot. So in fact, this weight or this force didn't change as you moved it up and down. Spring is different. Spring basically says, when I start pushing it, maybe it takes a little bit. When I push it a foot, it takes 10 pounds to hold it. When I push it 2 foot, it takes 20 pounds to hold it. So as I compress it more, I end up having to integrate, I get that. And so this is just accounting. It's just keeping up with 14. The problems in 14 are so incredibly simple that they're almost scary. So what you find out is chapter 12 had a lot of difficulty with a lot of these weird things. Polar coordinate stuff like that. That gets transferred into chapter 13 a little bit. It does not get transferred into 14. You'll find there are problems which are unsolvable in 12 and 13, which become easy in 14. And so that's energy. And then 15 is impact. people always say F, F is equal to ma. Okay, and so people look at that and they say, well, that's acceleration. But actually the equation is this. The problem is in the general public, you can't go around and say that in the general public. And the reason you can't is the first question that happens in the general public is, what is D? And why is there a D down there? And what is this T? Where did that come from? So in order to understand really what the law is, you have to have calculus first. So if the general population, if everybody that graduated high school was forced to take calculus, then the general population would not look at Newton's law like that. They would look at it the way it was supposed to be, which is this. But because the general population doesn't have calculus, this is how it was described. Just like, what is it? Oh, wait a minute. E is equal to mc squared, right? So at first glance, you look at that, you say, okay, it's written that way for one reason, because anybody can see there's a c and you can square it. Okay, what does square mean? Well, that means two of those. So that's pretty much easy to figure out for the general public, but it's much more complicated than that. And so what happens to you is you start with this concept in 15. And then what you find out is, wait a minute, I can do this. And now think about it like this. What happens if I have a force, which is a function of time? Okay, so say my force and time was, it moved out here, and it did like that. And I wanted to know, what's the velocity at that point? T1. What's the velocity at T1? Well, assuming that's 0, you would integrate from 0 to T1. And what you would do is integrate from mv at 0, mv, and actually I should do it like that, evaluated at T is equal to T1. It should be written like that. And you do this interval. And of course here, it's easy enough. You can figure out the area under that. They name that. They'll call it something called the I, or impulse. Some books just have it as I. I think this one has it as I. I've seen it written in books like that. And then all you're doing is looking at the left side. The right side. The right side's pretty easy. MV evaluated at T1 minus MV evaluated at T equals 0. I should say T is equal to T1. That is the right side. And so you're solving problems like that. What you find out is oh, wait a minute. This makes it so there's a whole set of different way of thinking, and you start thinking as f as a function of time and integrating. This lends itself next to going to play pool or going to play golf. Yeah, I don't know. Here. Okay, so here's your golf ball. And your golf club comes through here like this, and then the golf ball takes off and your club goes on that way. Impact. So you start dealing with impacts. And what is that? If you consider two, like during the impact of two pool balls, or the impact of a golf club and the golf ball, during that period, usually, now the golf club could be a little bit different, but during that period here, there's no other forces. So what you get is 1 and 2. You get M1, V1 initial, plus M2, being that second ball, V2 initial is equal to M, that's supposed to be M1, V1 final after impact, plus M2, V2 final or after impact. And so you get involved with that. And then there's another part that says, hey, I lose energy when I basically drop a basketball, it hits the earth, and it doesn't return to the same height. It's not a super ball, so it comes back to maybe here. So during that impact, I lose energy. And in that impact, there's something called coefficient of restitution that basically we deal with. That's how you figure out how much energy is lost during that impact. And that's pretty much it. We go through all that. I might try to touch on, okay, we're in 16. So I might try to touch on 17. And in 17, it's kind of strange, but we found the accelerations of like the piston and things. Once you find the acceleration of the piston, and you got this bar connected to it, you figure out, somebody tells you the mass of the piston. You just multiply that times your acceleration, you'll get the force that's on that pin that's holding that piston in that rod going back and forth. And so that's pretty much the entire semester. That's it. So what happens is 16 is the toughest thing to deal with, which is why I take it longer, and it's the most appropriate in the sense that you actually may use it as an engineer more than the other. But you need to know what happens in 12 and 13 and 14. Did I skip 15? No, 13, 14, 15, and then 16. That's right. So you need to know those things. You especially need to know energy, because you need to know if there's a problem that's unsolvable any other way, you may find it to be very easy to solve using energy methods. And once you start seeing that, you're like, crap, why did we not do this to begin with? But then you need to know the other stuff as well. So I hope that's it. So I spent just a few minutes laying out the rest of the whole semester. You'll find, I've talked about this before. I don't know if I did this. So 12 is difficult. 16 is a little bit more difficult. Then you get back to 13, and then the next chapter. And then the other one's kind of fun, so the hardness level goes down. So if you're struggling at this point, but you're getting it, the rest of it is going to be fairly easy to wrap up. So, and we're in November 4th, so the rest of it will go fairly quickly. So I hope I didn't waste your time, but if I did, let's check, and maybe they'll send you some refund on your tuition. I couldn't give you any refund because they don't pay me enough to give you a refund.